Imagine trying to understand this sentence if you could only see one word at a time with no memory of what came before. Impossible, right? Yet traditional neural networks do exactly that. They see each input in isolation. No context, no memory, no understanding of sequence. But language, music, stock prices, time series, they're all about sequence, about what came before influencing what happens now. This is why we need recurrent neural networks. And in the next 5 minutes, you'll understand them completely. From basic architecture to LSTM and GRU, with zero confusion. Let's understand the problem first. Traditional feed-forward neural networks have a fatal flaw. They treat every input independently. Show it the word bank, and it has no idea if you're talking about a financial institution or a riverbank. The context is lost. Sequential data has temporal dependencies. The meaning of now depends on then. In language, the previous words determine context. In time series, past values predict future trends. In music, the previous notes create melody. We need a network with memory, something that can carry information forward through time. Enter recurrent neural networks, RNNs. Here's the brilliant trick. RNNs have a hidden state, a memory vector that gets passed from one time step to the next. Look at the architecture. At time t, the RNN takes two inputs, the current input xt and the previous hidden state ht-1. It combines them, applies a transformation, and produces two outputs, the current output yt and a new hidden state ht. That new hidden state, it gets fed back into the network at the next time step. This is the recurrence. The network literally connects to its own past. The math is surprisingly simple. ht equals tan h of wh times ht-1 plus wx times xt plus bias. Then yt equals wy times ht. Three weight matrices, wh for the hidden-to-hidden connection, wx for input-to-hidden, and wy for hidden-to-output. These weights are shared across all time steps. That's crucial. When you unroll the RNN, you see the same network repeated over time. Same weights, same architecture, just processing different inputs at different moments. Let's trace actual data flowing through an RNN. Suppose we're processing the sentence, I love machine learning. At t equals 0, we feed I as a vector. The initial hidden state, h0, is typically zeros. The RNN processes it, outputting h1, which now encodes I. At t equals 1, we feed love plus the previous hidden state h1. The RNN sees both the new word and the memory of I. It outputs h2 encoding I love. At t equals 2, machine and h2 go in. Now the hidden state encodes I love machine. Each step, the context grows. By t equals 3, when processing learning, the RNN has seen the entire sentence up to that point. The hidden state h4 is a compressed representation of all previous words. This is how RNNs understand sequence. Each hidden state is a summary of everything that came before. Training RNNs is where things get interesting and challenging. We use backpropagation through time, or BPTT. The idea, unroll the RNN across all time steps, then backpropagate errors from the output all the way back to the start. At the last time step, we compute the loss. Then we propagate gradients backward through each time step, updating the weights. But here's the problem. Gradients must flow through many time steps. At each step, we multiply by the same weight matrix WH. If WH is large, gradients explode, growing exponentially. Your loss becomes infinity. Training crashes. If WH is small, gradients vanish, shrinking to 0. The network can't learn long-term dependencies. It forgets what happened 10 steps ago. This is called the vanishing gradient problem. It's why vanilla RNNs struggle with sequences longer than 10 to 20 steps. They have short-term memory, not long-term memory. Early words in a sentence, forgotten by the time you reach the end. Critical information from 100 time steps ago, lost forever. In 1997, researchers invented the long short-term memory, LSTM. It solved the vanishing gradient problem with a clever trick, gates. An LSTM has 3 gates. The forget gate decides what to throw away from memory. The input gate decides what new information to store. And the output gate decides what to reveal. These gates are learned. They're neural networks themselves, using sigmoid activations to output values between 0 and 1. 0 means completely block. 1 means completely allow. The magic? The cell state, a separate memory channel that flows through time with only additive operations. No multiplication by weight matrices at every step. This preserves gradients across hundreds of time steps. The formula CT equals FT times CT minus 1 plus IT times C tilde T, where F is forget gate, I is input gate, and C tilde is candidate memory. Then in 2014, Cho introduced the GRU, Gated Recurrent Unit. It's simpler than LSTM with only 2 gates, reset and update. Fewer parameters, faster training, often comparable performance. Both LSTM and GRU can learn dependencies over 100 plus time steps. They're the reason modern NLP works. RNNs revolutionized AI. Let's see where they're used. Language modeling, predicting the next word. GPT-1 used this. Give it the cat sat on the, it predicts mat. Machine translation, encoder-decoder RNNs. The encoder reads the source sentence, compressing it into a hidden state. The decoder unpacks that state into the target language. This was state-of-the-art until 2017. Speech recognition, LSTMs process audio waveforms, converting sound to text. Siri, Google Assistant, all used RNN-based models. Time series forecasting, stock prices, weather, sensor data. RNNs learn temporal patterns to predict the future. Video analysis, processing frame by frame, understanding actions over time. But RNNs have limits. They're sequential, can't parallelize across time. Training is slow on long sequences, and even LSTMs struggle beyond a few hundred steps. In 2017, transformers arrived. They replaced RNNs with attention, processing entire sequences in parallel. Now, most NLP uses transformers, but RNNs aren't dead. For short sequences, they're efficient. For streaming data, they're natural, and they taught us the power of memory in neural networks.